Okay, number 35. Pictures below should be above. These pictures represent particles. Which of these boxes contain mixtures? That's going to be B and D. B and D because those have different particles in them. 36. Which boxes contain pure substances? That's going to be A and C because those have identical particles. Of the boxes that contain pure substances, which contain compounds, which contain elements. So A and C are the pure substances. A is going to be a compound because it's two or more elements, and C is going to be an element because it's two identical atoms fused together. So A compounds, C elements. 38. 5 examples of pure substances. For each to indicate whether it's an element or compound. Well, let me just list a bunch of elements first. Carbon, hydrogen, oxygen, iron, nickel, cobalt, fluorine, iodine. There's plenty. There's 118 I could mention. Those are all elements. Compounds are when you have two or more elements fused together. So things like water, which is H2O. Things like table salt, which is NaCl. Things like sugar, C6H12O6. Things like carbon dioxide, CO2. Things like let me mention that one. Things like methane, CH4. Things like nitrogen dioxide, NO2. These are all examples of compounds. 39. 2 examples of homogeneous mixtures. You could talk about sugar water, which is most drinks. You could talk about salt water. You could talk about water with like food dye in it. You could talk about air, because air is a mixture of different gases and you can't really make out the particles. 40. 2 examples of heterogeneous mixtures. Things like pond water, because you could see the little particles floating around. Things like soil, because it's rocks and dirt and water and plants. Things like sand, because you could see all the different pieces. Things like trail mix, because you could see all the different components. 41. Physical properties. Things like density, solubility, malleability, ductility, magnetism, color, shape, mass, volume, conductivity of heat, conductivity of electricity, melting point, boiling point. These are all examples of physical properties. 42. Chemical properties. Flammability, reactivity. Those are really the 2 that we've talked about. 43. Is boiling a physical change or chemical change, and explain why. Boiling, like all of our phase changes, is just a physical change because you're not changing the atomic makeup of the substance. So if you take liquid water, that's H2O. If you boil it, you now have gaseous water, which is still H2O. So it's just a physical change. You're not turning into H2 and O2 or anything like that. 44. Name 2 other physical changes. Things like cutting something in half, flattening it with a hammer, sawing it in half. You can mention all the other phase changes, so melting, freezing, boiling, condensing, subliming, depositing. These are all physical changes. Dissolving something, that's a physical change. 45. 2 chemical changes. Things like anytime you react something. So if I take 2 chemicals and it makes an explosive reaction, that's definitely chemical change. Burning something, cooking something, when something rusts, when something tarnishes. These are all chemical changes because you're producing an entirely different substance. You're rearranging the atoms. 46. What is electrolysis? Well, it's a chemical change. It's a process in which you take water, you run an electric current through it, and it splits it up into H2 and O2. That's your chemical change. 47. Describe or sketch the difference between linear, branched, or cross-linked polymers. So linear is just like this. Branched is sort of when they have branches that sort of look like this. And so that's branch. I turn my linear into a branch. And cross-linked is when you have like two linears that are connected sort of like this, two or more linears. So that's like a cross-linked polymer. 48. Which of the three is the strongest? That's going to be cross-linked polymers because they're kind of held in that rigid, both directions hold. 49. Well, I should have also asked which is the weakest. The weakest is going to be branched. The second strongest is linear, because even though they're just like regular straight lines, you can bunch so many of them so close together that they become very strong. Branched is weak because the branches don't reinforce anything, and you can't really pack those very tight. Anyway, 49. One example of natural polymers, you could say things like DNA, RNA, cell walls, proteins, muscle, pretty much anything that makes up us or makes up any kind of animal or plant even is a polymer. 50. Synthetic polymers, so all types of plastics. Polyethylene is more a precise name for those plastics, so sometimes you see PE, like a HDPE, high density polyethylene. You could talk about things like bowling balls, nylon, polyester, PVC pipe, Teflon, Kevlar. These are all examples of synthetic or man-made polymers. 51. Three particles that make up atoms, that's protons, neutrons, and electrons. Nice and simple. 52. Charges. Protons are positive, electrons are negative, neutrons are neutral or no charge. 53. Where are they located? Well, protons and neutrons are in the middle of the atom. They make up the nucleus, and electrons orbit the outside. 54. For the following three elements, identify the atomic number and the atomic mass. For hydrogen, that's atomic number 1, means it has 1 proton, and the atomic mass is 1.008. For iron, Fe, that's atomic number 26, meaning 26 protons, and atomic mass is 55.847. And for carbon, atomic number 6, meaning 6 protons, and the atomic mass is 12.011. What is atomic number? That's 55. Atomic number is the number of protons. Very simple. 56. What is atomic mass? Well, atomic mass is like the weighted average of all the isotopes, or I should say of the mass of all the isotopes of an element. So we talked about carbon. Carbon has a couple different isotopes. C12 is what most carbon is, the vast majority. But some of it is a heavier isotope called C14. Note that since they're both carbon, they both have 6 protons. So this must have 6 protons and 6 neutrons. This must have 6 protons and 8 neutrons. So when you calculate atomic mass, you're not expected to do that, but when scientists calculate atomic mass, it's the weighted average. So if something like 99% of carbon is C12 and 1% of carbon is C14, it doesn't make sense to call the average atomic mass 13. It needs to be closer to 12. So that's why when you add all the carbon 12 and then a little bit of carbon 14, it ends up being 12.011 because it's very little of it. 57. Name 3 properties of metals that nonmetals do not have. You can mention things like high density, good conductors of heat, good conductors of electricity, ductile, malleable, generally dark silverish color. You could say they have high melting points, or they're generally solid at room temperature. 58. What are valence electrons? They are the outermost electrons in an atom. Why do we focus so much on them? Well, that's because they are the electrons that are involved in bonding. They're the only ones that are involved in bonding, so they're very important. 59. Lewis structures. So lithium, bromine, aluminum, neon, and oxygen. So to do Lewis structures, you need to put the number of valence electrons around each one. And to do that, we look at our periodic table, and you should have them labeled 1 through 18 by default, but also 1A through 8A. So this is 1A, 2A, skip all the way to this, and then 3A, 4A, 5A, and so on. Okay? And that number in front of the A is how many valence electrons. So lithium has 1 valence electron, so it gets 1 dot. Bromine has 7 valence electrons, so we go 1, 2, 3, 4, 5, 6, 7. Aluminum, 3 valence electrons, because it's in group 3A. Now the actual order in which you go doesn't really matter. Like you could have done here, here, and here. Doesn't matter. But what does matter is that you don't pair these up until you absolutely have to. The metaphor is like if you're a whole bunch of strangers are getting on a bus, they're generally going to each take an empty seat first before they go sit next to someone else. And electrons are the same way. Electrons are negatively charged, so why would 2 electrons want to hang out together unless they absolutely have to? 2 negative charges want to get as far away as possible. So like let's do neon here. It's 8 valence electrons, so the first 4 are going to go by themselves. You know, you don't want to put, you're not just going to put 2 together and leave it. So the first 4 go by themselves, and now we have to pair them up. So we go like this. So neon has 8 valence electrons, like that, and oxygen has 6. So again, what you don't want to do is this. That's not right, because why would these electrons want to hang out closer together than they have to be? So you end up doing 2 together, and then 2 separate, and then 2 more together like that. Okay. Number 60. Identify one element from each of the following groups. Alkali metals, that's group 1. So you could say lithium, sodium, potassium, rubidium, cesium, or francium. Don't say hydrogen though. Even though it's in group 1, it's not a metal, it's a non-metal. Hydrogen's over there way by itself. Alkaline earth metals, that's group 2. So beryllium, magnesium, calcium, strontium, barium, radium. Halogens, that's group 7A or 17. Fluorine, chlorine, bromine, iodine, astatine. And noble gases, that's group 8A. Helium, neon, argon, krypton, xenon, or radon. (61) Of the following groups, which would you consider to be reactive? Well, alkali metals. These are going to be very reactive. That's because they have 1 valence electron, so they're so eager to get rid of that one that they're going to dump it off on anything they can. So that's why you can take sodium and throw it in lake, and it's going to explode because that sodium is going to throw that electron at whatever it can. I would also say halogens are very reactive. Halogens have 7 valence electrons. They're so close to getting 8, which is what they want, that they'll steal that last valence electron from anything they can. So alkali metals and halogens all very reactive. 62. Non-reactive. That's going to be your noble gases. They are already full. They already have their full valence electrons. Most of these it's 8. The exception is helium with 2. But whether it's helium or any of these other ones, they have a full valence electron shell. They're done. They don't want any more. They don't want any less. So they're not going to react with anything. So that was 62. If you skip to 62, go back. I just talked about it. 63. Which ions do the following elements form? Beryllium. So beryllium has 2 valence electrons. it's going to form a 2 plus because it's going to lose those 2 electrons. And if you lose 2 negatives, you're going to gain 2 positive charge. Oxygen. Oxygen has 6 valence electrons. It's going to want to get to 8 valence electrons. So to do that, it picks up 2 negative charges. So therefore, O2 minus. Lithium is going to form Li plus. That's a 1 plus. We just write the plus because it has 1 valence electron and wants to lose it. So it's going to be Li plus. Krypton. Trick question. Krypton's a noble gas. It's not going to form any ions, so leave it blank. Aluminum. 3 valence electrons, so it forms a 3 plus. Nitrogen. 5 valence electrons, so it wants to gain 3 more to get 8, so 3 minus. Potassium plus. Fluorine minus. Sodium plus. Chlorine minus. Again, this all, you just have to look at the number of valence electrons. If it wants to gain valence electrons, like if it's a non-metal somewhere over here, well, it's gaining negative charges. So like chlorine is going to gain 1 negative charge, 1 electron. If it has like 1, 2, or 3 valence electrons, like if it's any of these or some of those, it's going to have a positive charge because it's losing negative charges. So like sodium, Na, has 1 valence electron, so it's going to kick 1 electron away, so it's going to lose a negative, gaining a positive charge. 64. Complete the grid. Okay. So writing our formulas here, you have to identify the charges on these, and that's going to tell you how they're going to bond together. You can't just write, like for number 3, you can't just say NaCl and just be done, although this is actually what it's going to be, you'll see. But like for example, for the next one, you can't just say AlO for aluminum oxide. You got to actually work it out. So anyway, let's go back to NaCl. Sodium is Na. It forms a +1 charge. Cl forms a 1 minus charge, and you could see a nice 1-to-1 ratio, a +1 and a -1. So these are just going to come together and form NaCl. The next one, we have aluminum, which forms a 3 plus charge, and we have oxygen, which forms a 2 minus charge. So this one, I said you can't just say AlO and call it aluminum oxide, because it's not balanced. A 3 plus can't cancel out a 2 minus. So what you do is you apply your crisscross rule, where that 3 comes down here, that 2 comes down here, and you get Al2O3. Or in other words, you need 2 of these aluminums to cancel out 3 of these oxygens. Alright, potassium and sulfur. Potassium is this, K+, sulfur is S2-, crisscross rule, K2S. Calcium is 2+, bromine is 1-, crisscross rule, CaBr2. Just like that, crisscross rule. Strontium and oxygen, Sr2+, O2-. By the crisscross rule, you would call it Sr2O2, but you're going to want to simplify that into just SRO. In other words, you can see a 2+ and a 2-, those are just going to come together in this real nice 1-to-1 ratio, so we get SRO. Okay, you don't want to write Sr2O2. Okay, number 65. We're now naming covalent molecules, so you have to use the Greek prefixes. So we have calcium tetrachloride, phosphorus trichloride, nitrogen dioxide, carbon monoxide, dinitrogen tetroxide. Remember, you don't say tetraoxide, you say tetroxide. Sulfur hexafluoride, and nitrogen pentafluoride. And finally, 66. What's the basic formula for a combustion reaction? Well, you start with a hydrocarbon, which is basically a long chain of carbons with hydrogens coming off, and so on. So carbon, 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 carbon with tons of hydrogens, plus O2 yields CO2 plus H2O. Now the idea behind this is you do need to put a little bit of heat into it. You can't, I mean, you could, hydrocarbon is like wood or oil or gas. If they're just sitting there, they're not just going to spontaneously combustion reaction. But if you give them a little bit of heat, they will. And what ends up happening is this does release a lot of heat. So you put a little bit of heat in, you get a lot of heat out, and you know, it seems like you're getting energy from nothing. You're not. You're getting energy that's kind of fused within the bonds of that hydrocarbon. But for a human perspective, it really is like free energy. We're applying a little bit of heat to get it to burn, but then we're getting tons of heat back out. And again, kind of the harm in this for us as society is look what it produces, CO2. That's our greenhouse gas, and that's why for 250 years humans have been doing this process. Or if you want to even consider the burning of wood, this process that's been going on for tens of thousands of years, hundreds of thousands of years. That it has led to a lot of CO2 up in the air, not naturally. Okay, so that's the end of the review guide. Thank you for watching.